Okay, so this seminar on imaging will serve two purposes. One purpose is that I just want to share with you some of the research that we've been doing lately that I think is interesting and I'd like to discuss with you. The second purpose is that it's sort of a consolidative act for a large collaborative project proposal writing with 30 plus PIs for SCCR, and so it's going to somehow serve also to maybe because of that I'll spend a little bit more time on introductory and maybe more programmatic notes than I would otherwise do. Okay, so I always try to insert Beatles in any story that I tell, and here it wasn't too hard. So towards the end of the 60s, these guys, the Fab Four, were busy recording their what turned out to be their last album, Abbey Road, which was named after the location of the recording studio in London, which was owned by a company named EMI Records. EMI stands for Electrical and Musical Industries. And as luck would have it, the same company also, it also ran a relatively small research operation, and it actually had a computer. And as I guess, as these guys were recording such hits as Mean Mr. Mustard or Oh Darling, in another part of EMI, there was a guy who was about to change the world of imaging forever in a very, very substantial way. So that guy's name was Godfrey Hounsfield, and he invented computed tomography, really. He jump-started the entire domain of computational image reconstruction, right? What he did was he realized that one could maybe reconstruct objects by shining X-rays through them at different angles, and then somehow compute from the resulting attenuations, the image of the object inside. Okay? And when I say that he invented a thing, I really mean that he both built the hardware with his own hands, okay, not necessarily every nook and cranny, and then he also made an algorithm and he implemented it on the PDP-9, that he was lucky to have there at the EMI, right? So he actually made an algorithm. And I'd argue that was a more important thing because at the time people knew about X-rays, and probably many people had this idea, but nobody actually made an algorithm and ran it on a computer to reconstruct an image, right? So it's very important for our talk. So here's one of the very first pictures that they made. First, he was experimenting with cow brains because he couldn't get anyone to, subject themselves to scanning by his machine. He did scan his own brain, and this is someone else's brain. This was actually very important because you can see a cyst here. It's like this darker area of unusual mass. And so the story goes that, he actually did this with his collaborator, who was a radiologist who was named Ambrose. And when Ambrose saw the picture, he said, "Do you know what you have done?" And then Hounsfield said, "Yes." That was at least, he seemed to be a cool guy. Okay, now ever since these first images were made, the entire domain of computational image reconstruction was driven by basically one complicated question, which is how can we get higher resolution, better images faster with less data of lower quality. Right? And the game is still on today. Really, machine learning and data-driven methods are in many cases and in many modalities now leading the way. But to understand how to answer this question, we need to know that there are really two components. One is the sensing component, and traditionally sensing component has been extremely important, right? It's the development of better sensors with better signal to noise ratio, with more pixels, better isolated, better calibrated, completely new modalities. This has really been driving the field. And then on the other hand, we have, what really Hounsfield did, that was algorithms. So development of new algorithms that somehow encapsulate both the physics of imaging and the properties of data that we're trying to image, right? And it's interesting to actually look at Hounsfield's algorithm, okay? So this guy was actually haunted by this thought experiment that maybe one could look inside the pyramids if one could measure, somehow the attenuation of cosmic rays passing through the pyramids. And the story goes again that at dinner parties, he would torture people with this story. But then to show that this is conceptually possible, he came up in '68 with this algorithm that would recover a 3x3 matrix of numbers from row sums, column sums, and the two diagonal sums. And this algorithm was iterative, and then they actually implemented it on the computer, actually for an 8x8 matrix. Now, of course, you can see, back at the time, many people knew how to actually solve this linear system, and also iteratively, right? So it seems that Hounsfield was not a great student, and that's what the accounts tell us, that he actually had bad marks and wasn't good at math. But he had enough drive to actually go and implement this algorithm and make it useful in some sense, right? And the algorithm was iterative, and it's very close to what we would, today call some sort of gradient descent or something. He would apply an adjoint with a forward operator, which is a back projection for those of you who know, and maybe I'll tell you later. and he would try to iterate out the error. Now, the question is, why do we need anything else than this algorithm? Right? This algorithm almost perfectly encapsulates what he knew about the physics of X-ray absorption. And the question is, why would we need other things? Why would we need more sophisticated algorithms? Right? So certainly Hansfield never asked, does this brain have 3 continuous derivatives, or is there a probability distribution of brains? And maybe I can get many, many samples of them and estimate, somehow this probability distribution and then build a model of the brain. No, he just used what he knew about physics at the time. Okay, and of course, we all know probably, or many of us, that the reason this is not enough is that the problems that we're trying to solve in computational imaging are typically rotten in the following way, right? They're not stable. And when you combine this lack of stability with the fact that there's always noise and that you always have missing data, then you get in trouble. And anyone can appreciate a simple example. So what you're measuring when you shoot X-rays to an object is attenuation, which is an integral of some quantity, like a logarithm of absorption, right? And so integration is a smoothing operation, right? When something goes in an integral, what comes out is nicer. It doesn't have these jumps. It's a smoother object. Now, of course, if you want to go back to the original thing, you're supposed to differentiate it. But there's always noise, right? So even if you add a tiny amount of noise to this, when you differentiate the result, you're just going to get junk. Oops. This is, I don't know how to use this, so I don't want to kill all the surprises. Okay, and so here's the result that you get. No, this doesn't work for some reason. Sorry, my computer has slowed down tremendously. Okay, I think I can stop here. Right, so even with the smallest amount of noise, you get a completely useful result. And so now, in order to get a useful result, we have to start making assumptions about what kind of object we're trying to reconstruct. Right? So historically, there are all sorts of assumptions that one can make that that are in some sense stronger and weaker. And so we can conceptualize this as sort of a trade-off, or a big spectrum of possibilities, where on the one end of the spectrum, we only use the physics of the imaging, of the forward models, and on the other spectrum, we only use data. And this is what somehow is the promise of the modern data-driven deep learning era, right? And physics side was what Hansfield did, and end-to-end deep learning is what this other completely data-driven extreme, at which maybe you can completely forget about any physics, you just get the data, operates. And over the years, between Hansfield and today, we had all sorts of we navigated this trade-off in all sorts of ways, right? So we had, we started making assumptions about how many regular derivatives you have. So we had Tikhonov regularization style things. We had sparsity-driven methods. Today we have end-to-end deep learning, and then we have all sorts of mixtures between the two, right? But one point that I like to make is that there exists an optimal kind of a Pareto curve that only learns what is really, really possible, what the physics and the stability constraints don't give us, right? And we are probably, as a field, very, very far from nailing this Pareto curve. So I think that is very important going forward. And so I'll try to organize my talk around these 3 questions. So the first one, I'll just show you some impressive results. If you have not seen them, you probably have, but so maybe it is redundant. But I just want to make a point that this purely data-driven strategy is annoyingly good, is extremely good, okay? But then I'll also show you that sometimes it just fails, and that the adoption of these things, both in scientific discovery and in medical diagnosis, is relatively slow because these things can hallucinate and they make certain assumptions about physics and data which are not materialized in practice. And then I'll tell you a little bit about some of our work on something that we call fancily generalized locality that addresses many of these points to an extent. Okay. So what is this, what is this end-to-end deep learning thing that I've been mentioning for a while, right? So the idea is that if you were Hansfield, then you knew that you have to put in a certain amount of computation to solve your imaging problem, right? You get your image, you know the physics, and then you have to compute, and then sometimes you have to compute a lot, depending on the instance of the problem. Now, what this other promise, the amortization, I call it, and I'll tell you why, is about, is that you can split the computation that you need to solve your problem into 2 phases. Now, the first phase is very slow, it's very laborious. You need a lot of hardware, a lot of data, you're toiling and you're sweating. But the first phase assumes that you have data. It assumes that someone gives you ground truth images, maybe, and also measurements. And these ground truth images and measurements are connected by the forward physics of the modality that you care about. And then you're just trying to fit some big, deep neural network to go back, right, to invert these images. And that's end-to-end deep learning. That is it. And you can do it in a smart way, or you can do it in a stupid way, but this is what it is about. Right? But then at the end of this first phase, you distill both, the knowledge of the physics insofar as it's needed to reconstruct an image, but also some sort of an ephemeral description of your data, of regularity, of, what does a brain or a knee or something look like. You distill this into a set of weights, numbers. Once you have these numbers, you can go to phase 2 that is fast and beautiful. You just do basically a constant amount of computation for any new piece of data that I bring you, for any new measurement, right? And I'd like to be sarcastic about this, but I cannot because this works extremely well. And I'm not an expert in MRI, and I'm also not an expert in CT, but I just gave you 2 examples that are just objectively impressive, right? So currently, state of the art, or one of the state of the art results in accelerated MRI, accelerated a lot, single coil, is an end-to-end trained deep network. This is from April this year. It's a really new paper. Now you read this paper and you see, this is just absolutely fantastic. You can speed up MRI scanning 8 times, and you can get images that are almost as good as not speeding it up. When you read this paper, what I find really interesting is that there is a huge amount of computer vision language. There's of course a lot of MRI talk, but when you read the paper, you really feel like you're reading a CVPR paper, right? Another example is from the group of Ulugh Kamilov on limited view CT. He was giving a seminar here not too long ago. Again, this is not exactly end-to-end deep learning, so I'm cheating a bit, but the results are just absolutely impressive. It is trying to learn an inverse of some forward map. And the results are, I could not believe when I saw them, how good they are. Right, okay. And then there is a completely different way. I just want to mention this for completeness, and especially because of this great, NCCR thing. A completely different way in which the technology of deep learning is being used these days is to come up with new parameterizations of images, not to learn inverse maps from measurements to reconstructions, but rather to just have a new model for image. Traditionally, we always work with arrays of pixels or voxels, right? And this is actually what a camera gives us. So it's a very convenient representation, but things are fundamentally continuous. And now you can actually use all the technology built around deep learning to build these continuous representations of, for example, images that you can fit to your data, and you can evaluate them at any continuous coordinate, up to floating point precision. And so in a few lines, you can instantiate a nice smooth surface like this, and then you can fit it to your image. And it seems trite, but actually it is profound for technological reasons. Because if now, for example, you need to deform this image, you only need to deform these 2 coordinates. You don't have to interpolate or do anything special. If you need to rotate it, it's trivial. If you want to take a derivative with respect to the input, to put this in some PDE that encodes your forward physics, it's trivial because the neural net gives you these derivatives, right? So somehow it has changed the dynamics of how we do things. And yes, you could say maybe it's a trivial thing to do, but here's, this thing originated in computer graphics communities and computer vision. So here is one example of an application of this. The video that you're watching there, this is not a real video. There's no pictures taken by a camera inside. This is a render from one of these big neural fields, right? So this is a fantasy of a neural net. And it's fitted to data, which is a bunch of pictures or videos by knowing, something about how light propagates, right? So it's solving an inverse problem. But this is an enormous scene, and this is absolutely impressive. I don't know if you have a sense, but this is absolutely impressive. Another example comes from cryo-electron microscopy. Again, these neural fields enable you to do things that were just very difficult, and so people just didn't do them before. Like, for example, you can say, I'm both going to parameterize my molecule, my density, scattering potential, whatever, continuously, but then I'll include additional coordinates, which will account, for example, for the conformational landscape, right? So the fact that proteins and protein complexes actually don't exist in one conformation, but in many. And I'll navigate this by navigating this latent space, right? This is, again, very, very fresh and very, very impressive. Okay, so despite all of these things, I'd argue that when, and I did this, okay, so I promise I did it, you pick up the latest issue of Nature or something, and you look for imaging-driven discoveries. They're still largely made with traditional reconstruction methods. There are examples where this is not true, for sure, but a lot of them are still made with traditional reconstruction methods. And here are some examples from like yesterday, right? So there's a cryo-EM paper, high resolution map of some complex that uses traditional reconstruction methods. I mean, traditional being extremely well-designed traditional methods, right? Which have a lot of technology around them, but not necessarily deep learning. There's a work from Manuel, who is, in the consortium that, we're writing this proposal with. And actually, I remember that the first talk in this seminar that I watched was from Manuel Guizar, and the impressive things that they do. And I was surprised to see that actually there was exactly 0 things based on deep learning, right? They use traditional algorithms which are carefully tuned for their amazing sensing, right? And so on. I mean, the same thing goes for medical. Whereas on the other hand, in the downstream pipeline, if you're a biologist, a PhD student in biology, I mean, your life has changed a lot in the past 10, 15 years because of deep learning. Because now, with the 0-shot and few-shot segmentation things, I mean, this student, they used to toil. They used to do this, I mean, menial tasks of manually labeling image. Oh, okay. Okay, yeah, so I'll just use this one. Yeah, so I mean, now it's so easy to segment images. This is work from a collaborator of mine. Also, segment membranes to do diagnostic deep learning, to denoise images. So everything downstream is really changing the lives of people who have to, analyze these images, just saving tons and tons of hours, right? And so the question is, how can we bring these two things together? Of course, the downstream needs the upstream, but somehow it still has not arrived, in my opinion, right? So there will be challenges to this claim. Okay, and of course, we can identify many reasons for that if it is true, but I'd like to talk about 3 in particular. One is that these methods are not stable. The other one is that we sometimes make assumptions about physics that are just not realistic. And the third one is that sometimes we make assumptions about data that are not realistic, right? So stability by now, I mean, I guess everyone has heard about it, but the point is that if you just train deep neural networks end-to-end to reconstruct images, for example, parallel MRI, this is relatively old by deep learning years now, but it's still an important example, is that sometimes these methods will reconstruct features that look anatomically plausible, biologically plausible, but they're not there. They're not true. And also they'll do the opposite. Another example is that this is from some of our work, is that they tend to overfit some structures in the images, something that Anders Hansen would call a false structure. In this case, you're training a unit to do something that is a standard way, originated from EPFL to reconstruct CT images. And if you train it, we know how to fix it in many ways, but I'm trying to make a point. So if we train it on chest CT and try to apply it to the brain or head, what you'll see is that the network is completely overfitted the large-scale structures of the chest, and the performance, absolute numbers are not so important, but the difference is important. Performance deteriorates a lot. And the reason is that this network is simply it wants to see the chest, right? So to speak, right? So how can we fix that? In particular, I mean, again, another person who gave a talk here, I think some 4 or 5 years ago, Anders Hansen, proved theorems. I mean, so it's a fact that if you do things a certain way, then you cannot avoid this. I mean, this will happen, even for samples that are in your training distribution, in the distribution of the data that you want to work with, right? So it's somehow fundamental. But of course, there are ways to avoid it by making assumptions, okay? And so we will be making assumptions. Okay, one possible assumption that we can make is that we don't have to do end-to-end deep learning because we know something about the forward models, right? And once you make this assumption, then you have to find a way to build forward models into your deep learning architectures. And we have beautiful, elegant ways to do this now. But many of these ways are really closing the loop. They're putting the forward physics in the loop. Now, there are 2 possible problems with that. One problem is that if you put the forward physics in the loop, you have to really believe that it's correct. And on approximation, well, depends on the resolution that you're aiming at. And you really have to make it very efficient, because otherwise your workflow will suffer, because training a network will take forever, and also inference will take forever. Okay. Now here's, we were thinking, okay, can we come up with some sort of an isolated toy setting where we can show how we can start correcting these things? An example being, maybe you train your network. You already put in the money, the cycles. And so now you have this reconstruction network, but it just makes some wrong assumptions, right? So can we still use this network at test time, at inference, to reconstruct high quality images? One example could be that maybe you don't know the sensing geometry. So you collect a sinogram, you collect measurements about an object. The sinogram is just, a collection of projections at different angles theta, and each projection is then a line, right? And so this sinogram is fundamentally a continuous object. right? We just sample, we must sample it. So we sample it at some discrete set of points. We assume that we know these points. Then we can, build a data set, train a network. Again, don't look at the absolute numbers, and it gives us a certain reconstruction. Well, this assumption is wrong. For whatever reason, we're applying it to a different geometry, maybe slightly different. Then we apply the same reconstruction method, and the reconstruction will deteriorate a lot, right? So this is an example where this kind of technological developments around AI and deep learning can really help us. So these neural fields that we can use to parameterize continuous functions, we can also use them to address this problem. And one way to pose it is like this, right? So there's this fundamentally continuous object, sinogram, which I call curly y there. And our measurements, discrete measurements, are obtained by sampling this fundamentally continuous object at some set of, at some geometry that we believe is true. So it's called gamma think. Okay, but in reality, this is what has happened. We sampled it at some other set of locations, which we call gamma true here. Okay, and so now what you can do, and this was possible also before the advent of deep learning, but it's so easy to do it now. And I think that is the game changer, is that you can say, well, okay, let me pose the problem so that I want to find some continuous underlying sinogram, which I call y hat, and also a set of sampling locations such that my data is actually explained by evaluating this estimated sinogram at the estimated set of locations, right, at the estimated geometry. But at the same time, I have trained this, reconstruction. I spent $1 million, right? So I really want to use it. I don't want to retrain it, okay? So when I applied to my measurements, I wanted to result in the measurements at what I thought were the correct locations, okay? And it turns out that to do this, conceptually is not too hard, right? So, really you can run this at varying levels of angle errors and varying SNRs, and you can see that, nailing, so accounting for this error greatly improves reconstructions. By the way, since Michael is not here, maybe I skip this spline comment that I had in store. Yeah, but we implemented the spline version of this. It also works well. Okay, so maybe you don't need it. But I had to torture my student to do that. So, okay. So another domain where something like this can really help is, or another situation is where actually the sample changes between acquisitions. And this is very common in MRI, but it's also common in something that they're more familiar with, which is cryo-electron tomography, right? So in cryo-electron tomography, you're shooting electrons to a small sample, very thin. And the sample is sensitive to the dose. So you cannot really irradiate it all you want because you'll just destroy it, right? And so even at the low doses that we currently use for imaging, the sample will, undergo this beam-induced motion between the different tilts. So here you're just tilting along a single axis. So you'll undergo, beam-induced motion for other reasons. Inelastic scattering will heat the sample will dome, all sorts of artifacts. And so basically the snapshots that you're taking from one angle to the other are different. And if you want to go to higher resolution, it's important to account for that. Again, like with this framework, you can simply parameterize, small deformations or diffeomorphisms of the domain of the entire reconstruction in a very simple way. You can just fit them together with the reconstruction, right? So here's a synthetic example. This is the, just going through the stack of projections. It looks like that, clean. This is what happens when you have a lot of, deformations and rigid motions between the frames. Here's something that people, one of the industry standards together with IMOD gives you a reconstruction and definitely, corrects for this motion. And then, here's reconstruction where it just fit this, neural net continuous both to the deformations and to reconstruction at once. Okay. Now, there are all sorts of fundamental questions about this, and I understand it, and we're working to address them. But the ease, I shouldn't say that. We spend a lot of time on it, but conceptual ease of doing this is now something that is changing the game. And there are a myriad of other parameters that one may wish to, reconstruct. So here's just a student project. I'm just going to tell you what it's about, and it's a bit contrived. So don't judge me because it's contrived. But the point is, suppose that you're operating an electron microscope, but you don't know the energy. You don't know the wavelength of your electrons. I don't know why that would happen. And then someone just hands you over a stack of projections and tells you reconstruct. Then you better know what energy we're operating at if you want to have a precise forward model. It turns out that you can do this just from the projections. Right? You can actually fit this one parameter. Now, contrived as it is, you can think that in these complicated instruments, there are a myriad of parameters that you only know approximately. So in some sense, if you know what you don't know and you can model it, this kind of framework really enables you to do crazy things. Yeah, so it's very exciting. Okay. And this brings me to the third challenge that we're facing, and that is important to push the field forward, which is that the default assumption in machine learning AI for imaging is that you have paired data, that you have access to ground truth images for any set of measurements, that someone also tells you in the training set, this is what you're supposed to get out of those measurements. Now, this is not always untrue. In two major cases, so culturally, this is an important and good assumption. So that's MRI and CT. When you're trying to accelerate these domains and you work close to a vendor, you actually do have many examples of fully sampled objects. Since your goal is to accelerate, you can just throw away some data and try to reconstruct the fully sampled reconstruction. So your network should do that, right? So in those cases, this is completely justified. But in things like molecular imaging, this is absolutely untrue. There was never a single cell that we could, shoot a lot of electrons at and then get a high resolution picture. We have 0 of those, right? So the only thing that we can deal with is actual data, is measurements, right? So there are maybe, 10 ways forward, but I'll talk about 2. One is to use simulated data. Now, if you have high quality simulators, both of objects and of forward physics, this can work, right? But you have to be careful not to overfit the simulated physics and not to overfit the simulated objects. The second thing is self-supervised learning, and that's just absolutely beautiful and elegant. So self-supervised learning is about looking for somehow symmetries, both of your data and of your physics, such that you can come up with losses that are non-trivial, but that you can use to train your networks. It's also, of course, what is driving things like large language models today. So that's very cool and very exciting. Okay, so now I just want to briefly discuss also how some of the work that we did on this generalized notion of locality may help overcome some of these challenges. And to tell you this story, first I have to go back in time, now 2 or 3 years. So back then, I was really excited about these neural fields and trying to understand, build sampling theorems from them, trying to use them for everything. And so we were using them in various projects. And so I asked a student of mine to try to come up with a generative model for discontinuous functions, right? There were generative models that spit out images on grids. So I thought, maybe it'll be hot stuff, and it, to an extent it was, to try to come up with a generative model for continuous images. So basically, if your image is represented by a neural network, this could mean, for example, that you have a generative model for the weights. That's sometimes called a hyper network. Whatever. Details are not important. What is important is that after a few, I guess, weeks, Amir came back to me and he said, I have a solution for you, right? So he said, the solution is we actually don't have to come up with this neural field thing because we already have generative models which can output, pretty good low resolution images. So we just need to do super resolution. And I was furious because I thought that he's trying to cheat me. I thought, this is not what I asked you. I know about super resolution. I really want a generative model for neural fields, right? But then when I thought about it a little bit more, I realized actually that what he was suggesting is much more profound because it's capturing something very, very important about why we can learn anything about images at all, right? It's capturing something important about why I can break the curse of dimensionality. This has been beautifully formalized in recent works of Stéphane Mallat and others, and I'll tell you a simple way to look at this problem. Okay, so first, let me show you what he did, right? So he basically, let me see if I have a slide for that. So he built an architecture that takes a patch of this image, but it takes a patch in any arbitrary continuous coordinate, and then just outputs a real value at the center of this patch, which is supposed to be the ground truth. Sounds trivial, right? Now there are major questions. Like one is how can you differentiate through this whole thing, taking out a patch, training the network to output this continuous coordinate, take the derivatives with respect to input, and so on. The other question is how are you supposed to train that? I mean, where you don't know what is there, right? That's the whole point of super resolution. So first, let me show you that this thing, once it's trained, it does something very non-trivial, right? So this network was trained. I apologize for the cell Bay data set. I always have to do this apology, right? But once you train this network, it's very hard to train a new set of networks, and so we're stuck. Anyway, I'll switch to other images later. But the network was trained on 256 cross 256 images. It has never seen anything in higher resolution, and now we use it to just oversample this image at a resolution 1024 cross 1024. And you can see that we are doing much better than something like interpolation in a silly way, right? You can call this a very smart data-driven interpolation. And technologically speaking, it's just very beautiful because you can again take the derivatives with respect to input coordinates. You can do whatever you want, like with a neural field. Okay, Now, the question is, how can you train this? And to train this, now we need to understand something deeper about the structure of image. And that is that what I made this insight was that at low resolutions, actually we have good generative models. That's good because at low resolutions, there is some stuff about the world that you just have to memorize, right? You just have to know that, a face has two eyes and they're usually above the nose, and then below the nose, there's a mouth. So some global geometry of a face, you just have to memorize. But once you know that, the remaining high frequencies or singular points of the image have a very special quality. And it is that they have a very, very, very simple spectrum, right? And because of that, imagine that you have a line singularity, which you're seeing through a camera. And so this is actually a perfect sharp line, right? You just happen to see it through a camera. And now you would like to zoom in, but you would not like to blur it, right? Because you know that actually under this, there is a sharp line, right? So you can maybe zoom in, this will make it broader. But now, because you know that it's just a simple line, there's a formula, there's a rule for the spectrum. Okay, so can you apply this formula to super resolve the next portion of the spectrum, and I get something like this, right? But this looks exactly like what I've started with. Okay, so I can again zoom in and apply the exact same rule, and then again it looks exactly like what I started with, right? So it turns out that a lot of images at high frequencies and a lot of physical fields have this beautiful symmetry, which Stefan Malak connected with the normalization group in physics, where they're regular over scales. So the rule that connects the scales is almost, not quite, but almost, constant. Right? It varies very slowly. And this is really what is behind this. So the way you can train any data is by doing the self-supervised thing. It's basically by downsampling the image that you obtain yourself and then trying to hop up scale by scale, right? And this actually works. Okay. Now, this clearly encodes the notion of locality, right? To super resolve around a given pixel, we're only using a neighborhood of that pixel. But the question is, how can we do this in a real inverse problem? Not super resolution of Celebi, but for example, cryo-ET or something like that. And for that, we have to change the way we think about locality. But let me just tell you why we might want to do that. It's this example that I've already shown you. If you train a deep neural network of a certain architecture and you train it on entire images, then typically, okay, so in the example of a computed tomography, what you typically do is the input of this network is also an image. And this image is obtained by applying some sort of a cheap inverse. And in this case, it's a filtered back projection. So you're mapping this image to this one here. Now, once you apply this fixed cheap inverse, a filtered back projection, it turns out that this information about any given pixel is spread with these streak artifacts. Information about any singularity is spread around the image with these streak artifacts. And so statistically, if you want to be strong in estimating a given pixel, you have to look at the whole image, right? And in some sense, what you need is a wide field of view, and this is why these networks work well. But once you have a large receptive field, then you tend to overfit to large-scale structures, right? Because they help you achieve a good MSE. Okay. And this is just to recall that this is actually the case. Now, here's how we can, again, use this locality insight, which is purely geometric, to come up with a very lightweight, very simple way to actually solve this problem and gain a lot along the way. And this is to look at the geometry of computed tomography, right? So if I want to reconstruct the image at a given point, then there is a particularly simple geometry that enables me to do that. In particular, I should look at all the lines, all the X-rays that are passing through this point. And then in the space of data, which depends on the angle at which I'm taking the projection, and on the coordinate along the projection, these lines, actually, each of these lines is a point on a sinusoidal curve. Here, because I'm only looking at the half angle, it's just a half the sinusoid, right? So modulo some filtering things that I can explain in detail, but I will not do it now. All the information that you actually need to perform an inverse is here, right? It's actually on this line, but maybe on a stripe, right? So there is no reason, in order to reconstruct this pixel, there is no reason to use this information, except some parenthesized way that I can explain later. Okay, so then this is exactly what we can do, right? So we can now say, okay, if I'm trying to reconstruct an image here, I can build something that looks like that function n, but that will look in a sinogram, okay, and then use a neighborhood of the information that I need. It needs to look at the filter sinogram. It uses a neighborhood of this piece of information and only processes this information in order to recover this pixel, right? And if you do that, you end up with something that's quite magical. You end up with something that performs almost as good as various state-of-the-art architectures. I'll try to go fast here. Sometimes it's worse, sometimes it's better, but it's on par. But this localization strategy it really gives you something that's absolutely great, which is that you can generalize very strongly out of distribution, right? So there's absolutely no problem anymore, right? And other architectures that generalize strongly out of distribution are all the ones that are actually using a forward operator many times during the reconstruction process. Here we are not doing it. We're just being mindful of the geometry of the problem that we are dealing with, right? As for experts, I can say that we also learned the filtering step in this filtered back projection, and this is actually very cute to look at. So what we do is basically, I can say 3 words about this. So the canonical inverse that Johan Radon already knew about of the radon transfer, this forward X-ray, imaging modality, is to apply some filter, like the one, that you do in signal processing 101, and then you do something very simple, which is called a back projection. So basically, you just integrate along that sinusoidal curve. Okay. Now, what we do is we keep this structure, but we learn the best filter, and we widen this little sinusoid into a stripe and learn the best reconstruction. Right? Now, the best thing, well, one of the good things, this is what I really, really like, is that when you do that, you end up with both statistical, computational, and all other sorts of benefits. Statistical, because you can generate much more training data, but also your network can be much simpler because it's taking a shorter input. So that's how you're dealing with the curse of dimensionality. But also it results in networks that have almost constant memory footprint when you go to high resolutions, like 1024 x 1024. Other stuff cannot, you cannot fit it in a GPU. So maybe you can, have multi-GPU things, but you have to get all fancy in order to work with that. And it's slow. Time per epoch when training these networks, here, whatever, 400 seconds. But here, it's impossible. Here we don't know, right? And that is very important because this actually enables end-to-end deep learning for real 3D problems, if you can build this geometry into these problems. And this is what I want to show you on the example of cryo-ET, this, modality that we can use to image cellular structures in situ, proteins, ultrastructure, and so on. Right? Okay, and one thing, so now we can try to train this network, but as I said in cryo-ET, we don't have any ground truth, right? And so the great thing about using localized networks is that, as I've shown to you, is that they are robust to overfitting, right? So now it seems much less dangerous to actually play with simulated data because it is much harder to overfit, right? And we'll see whether this is true or not. And so we use a simulator that's absolutely great. It's called cryo-Thomasim, that places particles and various ultrastructures in a volume, and then applies a very realistic forward model and generates projections for you. And now you see, this is just a generalization of the radon case. There is still some sinusoidal curve for any given point in the volume. There is still some sinusoidal curve in your data cube, which is now 3-dimensional. And what you have to do to generalize this notion of locality, you have to take a neighborhood of this sinusoidal curve in 3 dimensions. But now you can do it in real 3D. You don't have to do it slice-wise. You really take a 3-dimensional neighborhood slab of data, okay? And so here are some results. I'm getting close to being finished with everything. So we're experimenting with real tomograms of bacteriums called TQV. This is from our collaborators at the Biocentrum in Basel, Ben Engel's group. And maybe it's hard to see stuff here, so I'll zoom in. So here I'm showing you, so this is actually, we're doing a reconstruction that has been trained end-to-end on simulated data, and we're solving a real problem from real data, right? So this is what you get if you apply a standard reconstruction algorithm, filtered back projection. This is what you get if you do something that's like close to state of the art. It's what people in the industry use. And this is what we get. So the differences are maybe hard or impossible to spot on the beamer, but all these double membranes are much clearer. All the particles are clearer, ultrastructured, and so on, right? So we're really getting images that are about as good as state of the art. Here are some other examples, right, where I can zoom in. It's hard to appreciate these images unless you work in the field. This is the one that I like, so you can really see that it's close to this, maybe slightly better in some points. But the point here is that now we are not anymore doing some sort of post-processing like CryoCare does. We really start with raw data and we do a reconstruction. And what I learned by trying to do that is that it's really not easy, right? So if you start with raw data, there is so much stuff that goes wrong if you don't do a simulation that it's very hard to get any reasonable reconstruction, right? So I find this very exciting because these are the images that we've got over the past 1 or 2 or 3 weeks, right? So this, now we're at ground zero. We have a new toy to play with, and I'm sure that we're going to do interesting stuff. Okay, and so I think I want to tell you also about the theory of this, and I want to tell you also about applications in diffraction and radio astronomy and so on. but in the interest of time, I think I'll start wrapping up. So first, I want to open a parenthesis, which is that the whole shebang with the Beatles and CT, it really spurred quite a bit of academic discussion, heated debate about the funding of basic science in Britain. And papers were written about it with titles like, do we really need to thank the Beatles for the financing of the development of the computed tomography scanner, as well as the Beatles in life sciences, facts and fictions. This is a very, very good anthropological slant on the whole thing. So I'll just close the parentheses here. And now here's a serious wrap up. So I think if we really want to have, a step change in adoption, but also in the results that we can obtain with AI-based reconstruction, then we should just go ahead with what we propose, which is that we should stop hallucinating. We should really be careful that we can get the physics right. And we should basically forget in scientific imaging that we can get ground truth, because this is almost never true, right? Another thing that I want to mention is that when you want to build physics into your problems, sometimes the best way to do it is to really just put it in the loop, to close the loop, allow the forward propagation, and then you get something that is probably extremely good. But you need to have a very accurate forward model. Someone needs to write it for you, and you're gonna kill your workflow. It's gonna be very slow, right? Another way is like what we do. If there is some geometry associated with your problem, and for a huge range of problems, there is a geometry associated with them, then you can actually generalize what we've done. And we are already generalizing it to some things. We have, mathematical framework is called microlocal analysis. And, we can do interesting things. So that is one possibility. One thing that I feel is completely missing from the current AI for imaging landscape is to deal with truly, hopelessly nonlinear physics, okay? And what I mean by this is that maybe 10, 15 years ago, everyone was obsessed about convexity. And people were trying to produce images for linear inverse problems by constructing convex energies that would minimize and obtain images as a result. And the danger, like the place where you could become non-convex, was modeling your data. Like that's why people for sparsity used L1 norms, which are convex, and not more potent sparsifiers, which are not convex, right? So your data, the regularity, the description of your data could become non-convex. That could kill you, right? But the forward models were always simple and linear. But in fact, there are problems like strong multiple scattering, spectral inversions, etc., that are so hopelessly nonlinear that we cannot get any images. Regularization is not an issue. It's not that we're fighting for an extra nanometer of resolution. Getting any kind of image would be fantastic. And these problems exist, they're very important, but we just don't address them with learning because that is actually hard. Because we need to understand what kind of computational barriers exist. On the other hand, we know that deep learning, it solved Go, it's called AlphaGo, it solved protein folding, it's called AlphaFold, it solved many other combinatorial optimization problems, for which we know for a fact that they're computationally hard. So there is a hope in my mind that we could actually address these really, really rotten problems. It'll be hard, I don't know exactly how to do it, but I think it'll be fun. In the absence of very closing words, I'll reach out for the great wisdom of wiser people, which is that there's nothing you can do that can't be done. And so with that, I'd like to thank you for your attention.